type OS. It supports Windows and Linux very well so far. And the solution is that we build the information about each operating system object in the object file, which come in the debugging format, and we extract all those information from the debugging file at runtime. So here's about Windows. To support Windows, initially I rely on the React OS source code. Anybody here doesn't know React OS? React OS is an open source project that they try to build the open source OS that can run on the Windows application. So the idea is that if you have some Windows application, normally you have to buy Windows OS to run your application, right? So the idea is that if you have React OS, you can run your application, Windows application on React OS, and you don't need to buy Windows OS. That's the idea. And React OS is free and open source. It supports Windows 3000, 2003 and up. And you can see that to get the information from the Windows object, I compile the React OS file header with the debugging information. So you can see in the last slide, I use a GNU compiler, and I build my small program that include all the React OS prototype inside the code, and I compile it with a debugging option. And the idea is that with each version of Windows, I have one object file. So there's some problems. Because React OS so far only support Windows 2003 and up, so I need to patch the React OS header so it can support Windows XP and the version other Windows version before that. And I rely on Windows debugging simulator, which is open to the public. And besides that, really React OS, there are many problems in the information. First of all, there are many incorrect information in the React OS source code, so I need to fix the incorrect and not updated data structure from React OS, so we can support Windows Vista and Windows 2008, for example. And for the recent version of Windows, like Windows 7, React OS doesn't support, so I need also to patch React OS prototype header to support Windows 7. And here are some libdi API, so you can see that how we can use it to access to all the information from those objects. First of all, you can see that the top function di structure size. You can use this one to get the structure size if you give this function a structure name. You can also give the size of each member inside the structure if you use the second function di member size, and you need to give this function the structure name and member name. And even to get the offset of a particular member, you call the third function di member offset, and you give this function the structure name and the structure member. Here's a very simple code using libdi. That even to get the information from the Windows XP Service Factory version, I can call the function named di-open, and I open that object file for build for Windows XP Service Factory. And the next slide, I can call di structure size to get the size of E process structure. Next one, even to get the member size, the size of member create time inside the E process structure, I call di member size and give that function the E process and create time as a parameters. And lastly, you can see that I can get the offset of create time using the di member offset function. So it's very easy, and you can do that at runtime with own version of Windows. You can access to all the structure and all the member inside each structure. Okay, so after you can access, you can have the internal information of on those objects, you can use those information to actually extract those objects from the virtual from the memory with the virtual machine for you. So we design the API so it's very hard to be abused by the malware running inside guest virtual machine. So we design the API so that you can get the first object in the list object. For example, you want to get the list of all the kernel module inside the virtual machine. You call one function to get the first object, first kernel module, and after that you have another function to get the next kernel module inside the list, and so on. You repeatedly call that function to get the next object until you reach the last object. So here's some simple API from Nguyen Anh. For example, you want to get the first process inside in the list of all processes inside the virtual machine. You call the first function get task first, and this one returns the rest of the objects that keep the information about the first process in the memory. And after that, you call the get task next to get the next process inside the list, and you repeat that process again and again until you reach the last process inside the list of all the processes. And you can see that there are some other function to get the process ID. You can get the first DNN file opened by that process, and you can get the next DNN file in the list of all the DNN file opened by that process, and you can keep calling the last function until you get all the DNN file opened by that process. So here's a full architecture again. So you can at the bottom you have framework named libdi, and libdi can give you the access to the debugging information in all those objects I showed you before. And we support Windows object and Linux object so far, and you can see that in the middle layer. And on top of that, we have the actual API that extract all those objects from the memory for you. And here's a full picture again. So Inidor run at the bottom, and it gives you the access to the physical memory and virtual memory. And Inidor provide the service to Nguyen Anh run on top of that, and Nguyen Anh can access to the physical memory and virtual memory thanks to Inidor, and Nguyen Anh can return the information about all the objects inside the memory that you want to access to. And Equimolo is built on top of Nguyen Anh, and Equimolo can access to all the objects inside the guest virtual machine, and it can process the information and perform any action, for example, like scanning the memory to detecting malware inside the guest virtual machine. Yeah, that's a picture. So you can see that there are some other advantages provided by Equimolo. First, you can see that our scanner runs totally outside the virtual machine, and we don't need any support from the guest virtual machine. You don't need to install any agent inside the virtual machine. Just run the scanner outside, that's all. So it's very easy to deploy our scanner. And actually you can see that it has zero cost on deployment, because if you have, for example, a machine that run 100 virtual machine on that, normally you have to install 100 malware scanner inside each virtual machine. But now you don't need to do that, because you just run one scanner outside. So you have zero cost deployment advantage. Yeah, so about implementing Equimolo, as I said, we use a service provided by the below framework, Nguyen Anh, and you can access to all the OS objects inside the memory. And after we have all those objects, we perform many tactics to detect malware. First one, we use a method named baseline detection. So the idea is that you create a baseline when you know that the system is clean. And after that, in the future, if you want to detects the malware inside the virtual machine, you scan the virtual machine and you compare the result with the baseline. And if you see something not in the baseline, you can report. It can be malware. So you can see that we need to define baseline for the clean system. You can have baseline about the kernel module, about system code, about processes, about connection network, and something. Besides baseline detection, we have another detection method named cross-view detection. And the idea is that usually when the attacker installs the rootkit inside your system, the rootkit will try to modify your view, so you don't see the rootkit anymore. But usually the rootkit is not perfect, so if the rootkit modifies something and you don't see that anymore, but you can see that from another view, and you can still see that information. For example, there are some rootkits that try to remove one process from the list of all the processes in the memory. But if you look at the list of all the processes in the memory from different view, you can still sometimes see the different view, different result. And they call this detection method named cross-view detection. So you compare critical system objects from different point of view, and if you see the difference between views, you can see that something's wrong inside the system, and it can be rooted. So far we perform cross-view detection on processes, threads, DNN, kernel modules, network connection, and the port. The third detection method we employ in Equino is black and whitelist checking. So the blacklist detection is very simple. You know for sure that if you see something inside your system, you know that that's rootkit, that's malware. For example, some well-known malware can install some well-known kernel module inside the system. So when you see the list on the kernel module and you see one that is well-known from malware, you can see that your system is infected, right? So basically, blacklist detection method, we list on the known bad object, and if you see something in the blacklist, you can report as malware. But you can see that sometimes we still have many false positives, so we have another checking named whitelist. So in the whitelist, you list on the exception that should not be reported. So you can use whitelist checking to eliminate many false positives that the malware scanner can report. And the final detection we use in Equino is named abnormal behavior detection. So basically that the rootkit can modify your system in many places, in many critical places. First of all, it can modify the import arrestable, export arrestable inside processes, inside kernel module, inside the DNN, inside they can modify system code. So the idea is that if you see the information that should not be like what it is, you can report. For example, normally the system code on the system code arrest should point to one kernel module inside the Windows. And when you check on the system code, and if you see one system code point to somewhere else, not into that kernel module, you can report, right? Because that's abnormal things. And you can do the same detection on the other type things like IDT, GDT, import arrestable, export arrestable, and many other things. And here's a detection model. You run the baseline detection first, but actually baseline detection can be optional, because in fact you don't always have baseline. So if you don't have baseline, you can ignore this step. But if you have that, you can run baseline detection, and this one can report the malware. And cross-view detection can also report malware. behavior detection can report malware, blacklist, whitelist detection